This is a modern Lamborghini engine block, a masterpiece of specialized alloys and computer-aided design, built to withstand extreme forces unimaginable just decades ago. But while the outer shell is futuristic, the physical sequence of events happening inside this machine is surprisingly old. In fact, it was perfected long before the first computer was ever built. This creates a strange technological contradiction. We have spent a century and a half reinventing every other part of the car, yet we are still relying on a power sequence invented in 1876. Why has this specific design proven so difficult to replace? In the early 1800s, engineers were desperate to find a way to move goods and people without relying on horses. At the time, the only real solution was steam power, the same technology that ran massive factories and locomotives. But steam engines rely on external combustion. You have to burn coal outside the engine to boil water, which then creates the pressure needed to move a piston. This required massive boilers, heavy piles of fuel, and constant water refills, making it physically impossible to build a small, personal vehicle. The first major pivot came from Etienne Lenoir. He realized that if you could burn the fuel directly inside the cylinder, internal combustion, you could eliminate the heavy boilers and the coal entirely, radically reducing the weight of the machine. While Lenoir proved the concept could work, his engine was incredibly weak. It was too inefficient to actually pull a vehicle, leaving the industry with an engine that was lighter than steam, but not powerful enough to be useful. Proving that a fire could burn inside a cylinder was only the first step. The real challenge was taking that explosion and making it efficient enough to move a person through the world. In 1876, German engineer Nikolaus Otto arrived at a crucial realization. He understood that to generate real power, the fuel and air mixture couldn't just be lit on fire, it had to be specifically prepped before ignition. He developed a four-step process. The intake stroke moves the piston down, drawing in fuel and air. Compression squeezes the mixture. The power stroke creates an explosion, slamming the piston down. Finally, the exhaust stroke pushes burned gases out, clearing the chamber. This four-stroke sequence solved the power-to-weight problem. It was an architecture small enough to sit on a chassis, yet strong enough to move it, a design that would define the next 150 years of transportation. While Otto's engine worked in a workshop, it was Carl Benz who first successfully integrated it into a moving machine in 1885. This original patent motorwagen shows how rudimentary those first steps were. It used a single-cylinder engine and a large flywheel to keep the motion smooth, reaching a top speed of just 16 kilometers per hour. At the same time, Gottlieb Daimler and Wilhelm Maybach were refining the engine even further, focusing on increasing the internal speeds and reducing the overall weight of the components. By mounting Otto's stationary invention onto wheels, these engineers turned a mechanical experiment into a global race for automotive speed. In the 1890s, Rudolf Diesel looked at the four-stroke cycle and wondered if he could push the physics of compression even further. Diesel's idea was to remove the spark plug entirely. He realized that if he squeezed the air inside the cylinder hard enough, the heat from that pressure alone would be enough to ignite the fuel the moment it was injected. This method required much heavier engine blocks to survive the extreme internal pressures, but it was incredibly efficient. Because of that raw strength, diesel engines quickly became the default choice for global shipping and heavy industry. By the start of the 20th century, the two paths of modern transport were set: gasoline engines for speed and light travel, and diesel for the heavy lifting of global commerce. As the 20th century progressed, the production of these engines scaled to an industrial level that changed the physical layout of our cities and our lives. Engineers spent decades adding sophisticated accessories to the engine. Electric starters replaced hand cranks, turbochargers added more air, and computers took over the timing. But despite the shift to high-tech sensors and digital management, the actual physical sequence generating the power hasn't changed. The four strokes Otto designed in the 1870s are still doing the work today. In many ways, the last century of automotive history hasn't been about inventing a new engine. It's been about perfecting a 150-year-old idea with better bolt-on parts. Now, for the first time in over a century, that dominance is under threat. The internal combustion engine is finally facing a technology that doesn't just improve on its design, but replaces it entirely. Electric vehicles and hydrogen fuel cells are beginning to replace the gas station infrastructure. These technologies move vehicles without needing the thermodynamic cycle that has powered us since the 1800s. While the future of transport may be silent and electric, the world we live in today was quite literally built by the force of controlled explosions. For 150 years, the expansion of the modern world relied on this specific mechanical sequence. As that sequence finally begins to disappear from our roads, it concludes a run of mechanical dominance.